For all of human history, are we alone? Was just a guess. Today, it might be a fact. James Webb hasn't just found another planet. It has detected a chemical fingerprint with 99.7% confidence, a specific molecule that, on Earth, is only produced by life, floating in the sky of a world 120 light-years away. Get ready, because we might be standing on the edge of the greatest discovery of all time. And before we decode this signal from deep space, tell me, where are you connecting from right now? Comment your city and current time down below. Let's see who is awake with the universe tonight. Some 120 light-years from our own world, nestled within the constellation Leo, an observation has been made that promises to fundamentally alter our perspective on life in the cosmos. Data from the James Webb Space Telescope points to a distant world with a steady temperature of 120 degrees F, enshrouded by an atmosphere that shows the chemical fingerprint of biological activity. Researchers express a confidence level of 99.7% in their findings, which suggests the existence of a planet that may not only harbor life, but could offer conditions even more stable for it than Earth. The pivotal information came through on a Tuesday in December, concealed within vast terabytes of infrared data gathered by our most advanced observatory in space. At Cambridge University, Niku Madhusudhan sat before his computer screen, analyzing the wavelengths of light that had journeyed for 120 light-years to reach his instruments. What he observed was enough to cause a profound reaction. There, within the light spectrum that had passed through an alien world's atmosphere, was a signature that seemed out of place. The molecule was dimethyl sulfide, a compound that, based on our experience on Earth, is exclusively generated by biological processes. This was not a faint trace. The signal was so pronounced that the probability of it being an error was calculated at less than 3 inches 1,000. The James Webb Space Telescope had seemingly accomplished what generations of scientists had only imagined, finding compelling evidence of life beyond the confines of our solar system. The planet, which carries the designation K2-18b, orbits within the habitable zone of a red dwarf star, a region where conditions could allow for liquid water. This world, however, is profoundly different from anything we know locally. It is 6 times more massive than our planet and is enveloped in a hydrogen-rich atmosphere. This atmospheric composition creates a uniquely effective greenhouse effect, allowing immense oceans to stay liquid under its foreign skies. The temperature measurements themselves were remarkable, registering 120 degrees F, a climate warm enough to encourage life to thrive, but not so hot as to cause the planet's water to boil away. Madhusudhan and his colleagues had been observing this world for months, leveraging the JWST's extraordinary sensitivity to analyze its atmosphere as the planet transited its star. With each pass, new details emerged. The first discoveries were of water vapor, followed by methane, and then carbon dioxide. But the presence of dimethyl sulfide was the critical finding. This particular molecule is so closely tied to biology that its detection in an extraterrestrial atmosphere is akin to finding a clear beacon announcing the presence of life. The realization of what this meant was a moment of immense significance. If these results are verified, the discovery could mark the end of humanity's perceived solitude in the universe. We would have a powerful indication that we are not alone. The statistical analysis was impressive, yielding a 99.7% confidence that the signal was genuine and not the result of instrument noise or some form of contamination. Within the field of astronomy, where absolute certainty is a rarity and initial findings are often revised, such a high degree of confidence is exceptional. K2-18b is a particularly interesting candidate, as its distinct properties could make it even more suited to sustaining life than our own planet. Its dense hydrogen atmosphere serves as a massive insulating layer, trapping warmth and fostering stable conditions across the globe. In contrast to Earth's relatively thin nitrogen-based atmosphere, This substantial hydrogen blanket could maintain liquid water over a much wider array of temperatures and pressures. The host star, K2-18b, is a red dwarf, which is smaller and cooler than our Sun, but also significantly more long-lived. Our Sun is destined to expand into a red giant, which will one day extinguish all terrestrial life, whereas red dwarfs can burn steadily for trillions of years. This provides a vast, stable timescale for any potential life on K2-18b to evolve, perhaps reaching levels of complexity far beyond our current understanding. As Madhusudan readied himself to announce the team's research, he understood that this particular December morning could be remembered as a turning point in history, the moment our species found the first strong evidence that it might share the cosmos. This, however, was merely the start of a new chapter that would reshape our comprehension of life, the universe, and our own position within it. For a long time, the scientific consensus was that we needed to locate an Earth twin, a rocky planet orbiting a sun-like star at the perfect distance to support liquid water. K2-18b has completely dismantled that narrow assumption. This world demonstrates that life might arise under circumstances so alien that we had not previously considered them viable. The planet is classified as a super-Earth, a category for worlds that are larger than our own but smaller than Neptune. Not long ago, astronomers tended to write off such planets as inhospitable gas worlds, believing their high mass would preclude the existence of life as we know it. The case of K2-18b has compelled a total reconsideration of what a habitable planet can be. Its mass results in a surface gravity almost 3 times that of Earth's. An individual who weighs 150 pounds on Earth would feel as if they weighed over 400 pounds on K2-18b. Paradoxically, this intense gravitational pull might be advantageous for life. The strong gravity holds the atmosphere firmly, preventing it from escaping into space, a fate that befell Mars billions of years ago. The atmosphere itself challenges our conventional models of habitable environments. It is dominated not by the oxygen and nitrogen we breathe, but by hydrogen and helium. On our planet, hydrogen is a minor trace gas, accounting for less than 1 part per million of the air. On K2-18b, hydrogen makes up the great majority of the atmospheric volume, resulting in a truly alien setting. This hydrogen-based atmosphere establishes what could be described as a reverse runaway greenhouse effect. Rather than overheating the planet to an extreme like Venus, the hydrogen functions as a near-perfect insulator, ensuring consistent temperatures across its surface. The thick atmosphere is so efficient at redistributing thermal energy that even the planet's night side, permanently turned away from its star, stays warm enough to support liquid water. The collection of chemical signatures detected by the JWST suggests a world where life has not only appeared but is flourishing. Alongside the life-indicating dimethyl sulfide, the atmosphere holds methane, carbon dioxide, and water vapor, a mixture of molecules indicative of active biological systems. Here on Earth, these very gases are cycled by organisms ranging from microbes to complex life, creating a planetary metabolism that is detectable from afar. Yet, what is absent from K2-18b's atmosphere is perhaps just as telling. The lack of ammonia, a molecule that should be abundant if the planet were simply a lifeless gas giant, offers compelling evidence that biological processes are actively scrubbing it from the air. Life on this world may not be a passive passenger. It appears to be an active participant in shaping the chemistry of its own atmosphere. The discovery centered on K2-18b opens up the possibility that the universe is rich with life, thriving in environments we are only now beginning to imagine. Should life prove capable of emerging and thriving within the hydrogen-rich atmosphere of a super-Earth, the galactic census of potentially habitable worlds could expand by a factor of hundreds. Red dwarf stars, such as the one K2-18 orbits, suddenly shift into focus as primary candidates in the search for life beyond our planet, a significant development given they constitute 3/4 of all stars in the galaxy. The implications of this are truly profound. It suggests our search may not be for an exact counterpart to Earth, but rather for a kind of unfamiliar cosmic relative, flourishing in an environment so foreign that we are only now starting to comprehend its potential. The James Webb Space Telescope represents more than just humanity's most powerful orbital observatory. It is an instrument that looks back in time, peering deeper into the universe than any device constructed before it. Positioned 1,000,000 miles from our world at a point of gravitational equilibrium known as L2, the Webb telescope operates in a state of unending night. Its enormous sunshield perpetually blocks the heat and light from our star, ensuring its sensitive instruments remain at temperatures colder than the surface of Pluto. The telescope's main mirror spans an impressive 21 feet in diameter, a width nearly 3 times that of the Hubble Space Telescope. Yet, its revolutionary power is not a matter of size alone. This mirror is an assembly of 18 hexagonal segments, each one coated in an infinitesimally thin layer of gold, which allows it to reflect infrared light with an accuracy never before achieved. When these segments function in unison, they form a reflective surface so perfectly aligned it could discern the thermal energy of a bumblebee resting on the moon. While infrared light remains invisible to our eyes, it holds the essential clues for identifying life on distant planets. As a planet transits its star, a minuscule portion of the starlight passes through its atmosphere on its way to Earth. Within that atmosphere, different molecules absorb very specific wavelengths of infrared light, leaving behind unique chemical fingerprints that Webb is designed to read with extraordinary sensitivity. The difficulty of detecting these molecular traces is almost beyond comprehension. It is analogous to attempting to spot the glow of a single firefly next to a brilliant searchlight from a distance of 1,000 miles. The star K2-18 is billions of times more luminous than the planet that circles it. Yet Webb can isolate the faint infrared signatures of molecules within that planet's atmosphere with remarkable precision. A key technological advantage for Webb is its coronagraph instrumentation, which was initially developed to obscure the blinding light of stars and thereby reveal dimmer objects hidden in their glare. Through advanced image processing, the overwhelming brightness of the star is digitally subtracted, leaving only the delicate infrared traces of molecules in the atmosphere. The process is like applying a highly sophisticated filter to cancel out the roar of a jet engine, making it possible to hear a whisper just beneath it. The identification of dimethyl sulfide on K2-18b required the Webb telescope to perform at the absolute edge of its design capabilities. This particular molecule leaves an infrared signature so faint that its confirmation required numerous observations conducted over a period of several months. Each of these observation sessions captured only a handful of photons that had journeyed 120 light-years across the void of space, carrying with them information about the possibility of life on another world. However, Webb's most stunning accomplishment may be its capacity to measure temperature with such incredible exactitude. The telescope determined that K2-18b has a stable surface temperature of precisely 120 degrees F, which is warm enough for liquid water to exist, but not so hot as to cause it to boil away. This temperature measurement, accurate to within a few degrees across the vastness of interstellar space, stands as one of the most precise environmental readings ever taken of an exoplanet. The data analysis needed to pull these findings from raw infrared observations relies on some of the most sophisticated computer algorithms ever created. Systems driven by artificial intelligence sift through millions of individual data points, identifying patterns so subtle they would be entirely missed by human analysis. The discovery of potential life on K2-18b is not merely a monumental achievement in engineering. It is a testament to our species' drive to expand the boundaries of the possible. The Webb telescope has fundamentally altered our connection to the cosmos. We have moved beyond simply asking if life exists elsewhere. We are now in the process of observing its signs, That figure, 120 degrees F, seems almost too ideal to be a coincidence. It is the temperature of a sweltering summer afternoon in Death Valley, the comforting warmth of a hot tub, or the elevated heat of a human body combating an infection. On K2-18b, it is the temperature that could enable life to exist on a global scale. Temperature is a critical factor for life as we know it. If conditions are too cold, water turns to solid ice, halting the complex chemical reactions that life depends upon. If they are too hot, water evaporates into steam, rendering a world a sterile desert. The specific range where water can remain liquid, which scientists refer to as the habitable zone, is remarkably narrow. Our own planet happens to occupy a position almost perfectly in the center of our sun's habitable zone, a fortunate cosmic circumstance that has permitted life to thrive for billions of years. But the ideal temperature on K2-18b is not a matter of chance. It is the product of an intricate interplay between the energy from its star and the chemistry of its atmosphere, which together forge conditions far more stable than those on Earth. The planet orbits its red dwarf star at just the right distance to receive nearly the exact same amount of energy per square meter that Earth does from our Sun. This remarkable coincidence means that, despite being 120 light-years away, K2-18b is situated in a thermal environment that is fundamentally similar to our own. Its hydrogen atmosphere is essential for preserving this perfect temperature. In contrast to Earth's relatively thin nitrogen atmosphere, which allows heat to radiate away into space quite easily, the dense hydrogen envelope of K2-18b functions like an insulating planetary blanket. Hydrogen molecules are effective at trapping infrared radiation, which generates a greenhouse effect that keeps the planet consistently warm, even on its night side, which is in permanent darkness due to the planet's tidal locking. This thermal stability results in something with no parallel in our own solar system, a world where liquid water could potentially be found everywhere, from the side in perpetual daylight to the side in eternal night. Here on Earth, the temperature differences between day and night, between the seasons, and between the poles and the equator give rise to intricate weather systems and distinct climate zones. On K2-18b, the thick atmosphere is so efficient at redistributing heat that the entire globe likely maintains a uniform, life-friendly temperature. The consequences of this for any potential life are immense. Terrestrial organisms experience stress from temperature fluctuations, which forces them to adapt to seasonal shifts, migrate to escape the cold of winter, or evolve complex biological systems to maintain their internal temperature. On K2-18b, life might not have to contend with any such challenges. A consistent temperature would allow organisms to invest their energy in growth, reproduction, and evolution, instead of focusing on mere survival. What is particularly intriguing is how the 120-degree temperature on K2-18b falls within a range where familiar life could not just survive, but actively flourish. Experiments in laboratories have demonstrated that biological processes can operate efficiently at temperatures up to 250 degrees Fahrenheit. At 120 degrees, chemical reactions happen quickly enough to support complex metabolism, all while staying cool enough to keep essential biological molecules from breaking down. The discovery of K2-18b's ideal temperature represents more than a scientific curiosity. It is proof that the cosmos can fashion conditions for life that are not only habitable, but perhaps even more hospitable than Earth. In a universe where most planets are either frozen expanses or molten infernos, K2-18b stands out as a symbol of hope, a world where life might not just endure, but thrive in perfect comfort. Dimethyl sulfide. The name may sound like a chemical puzzle, but these two words could represent the single most important finding in human history. When the James Webb Space Telescope identified this molecule in the atmosphere of K2-18b, it found something that has never been created by any known non-biological process. It discovered the signature of life itself. On our own planet, dimethyl sulfide is produced solely by living organisms. Phytoplankton in the oceans generate this molecule as a byproduct of their metabolism, releasing it into the atmosphere where it helps shape cloud formation and weather systems. Marine bacteria, certain algae, and even some plants create dimethyl sulfide as part of their normal biological functions. Yet no geological activity, no chemical reaction, and no non-living system has ever been observed making this molecule. The detection of dimethyl sulfide on K2-18b is revolutionary because it is what scientists refer to as a biosignature, a molecule that can only be made by life. Unlike oxygen, which can be formed by non-biological means, or methane, which can seep from geological formations, dimethyl sulfide has no recognized abiotic source. Its presence in K2-18b's atmosphere is as near to definitive proof of life as we can achieve without directly seeing the organisms responsible for it. The molecule's chemical structure speaks to a story of biological complexity. Dimethyl sulfide features sulfur atoms bonded to carbon-based methyl groups, a combination that requires specific enzymes to assemble. These enzymes evolved on Earth over billions of years, developing as a component of the sulfur cycle that regulates our world's atmospheric chemistry. The fact that similar molecules are present on K2-18b suggests that life there has also developed sophisticated biochemical pathways. But the most astonishing aspect of the discovery is the sheer abundance of dimethyl sulfide in K2-18b's atmosphere. The concentrations detected by Webb are vastly more concentrated than what would be anticipated on a planet where life was just beginning. This implies that biological processes on K2-18b are not just present, they are flourishing on a planetary scale. The ramifications are profound. If life on K2-18b is producing dimethyl sulfide at levels that can be detected from 120 light-years away, its biosphere must be enormous. We are not speaking of microscopic organisms struggling for existence in isolated enclaves. We are talking about a planetary ecosystem so vast and productive that it is actively reshaping the chemistry of an entire world's atmosphere. This finding also poses deep questions about the nature of life itself. If organisms on K2-18b are making dimethyl sulfide, they must have evolved biochemical pathways that resemble those on Earth. This suggests that the fundamental chemistry of life, the utilization of carbon, hydrogen, oxygen, nitrogen, and sulfur to construct complex molecules, might be universal. Life may not only be common throughout the cosmos, it might also follow predictable patterns wherever it emerges. The detection of dimethyl sulfide is more than a scientific breakthrough. It marks the moment humanity learned we are not alone in the universe. Somewhere, 120 light-years away, under alien skies and in hydrogen-rich air, life is breathing, growing, and fundamentally altering the chemistry of its world. For the first time in human history, we have tangible evidence that life exists beyond Earth. In the scientific realm, certainty is an exceptionally rare and precious thing. Scientists communicate in probabilities, statistical confidence levels, and margins of error. They hedge their conclusions, qualify their statements, and acknowledge what is unknown. Yet when the James Webb Space Telescope data on K2-18b was analyzed, the numbers told a story so clear that even the most conservative researchers could not ignore it. There was a 99.7% chance that the dimethyl sulfide signal was real. To understand what this means, consider flipping a coin 1,000 times. The probability of getting heads or tails on a single flip is 50%. But the probability of getting heads 997 times out of 1,000 is so incredibly small that it would never happen by chance in the entire history of the universe. That is the level of statistical confidence scientists have in the detection of life on K2-18b. This confidence level is derived from a sophisticated statistical analysis called sigma detection. In particle physics and astronomy, scientists use sigma levels to determine how likely it is that a signal represents a true discovery rather than random noise. A 3 sigma detection means there is a 99.7% chance the signal is genuine, with only a 3 inches 10,000 chance it is a false alarm. This is the same statistical threshold used to discover new subatomic particles, confirm the existence of gravitational waves, and validate the most important discoveries of modern science. However, reaching this level of confidence for an exoplanet's atmosphere required unprecedented precision. The dimethyl sulfide signal is extraordinarily faint, just a few parts per billion in the infrared spectrum. To detect it, Webb had to measure wavelengths of light to an accuracy of 1 part in 10 million, which is like measuring the width of a human hair to the precision of a single atom. The analysis involved multiple independent observations over several months, each one confirming the presence of the dimethyl sulfide signature. Different instruments on Webb detected the same molecular fingerprint at different wavelengths, providing redundant confirmation of the discovery. The conclusion that life may exist on K2-18b is built upon an exceptional foundation of statistical analysis. To reach this point, every plausible non-biological source for the detected dimethyl sulfide signal was meticulously investigated. Powerful computer algorithms sorted through millions of data points, searching for any systematic errors or contamination that might create a false positive, but that exhaustive search found nothing. The statistical review also weighed a host of alternative explanations. Could the signal be the result of some unknown atmospheric chemistry? Was it possible it was contamination carried from Earth? Could it simply be an instrumental artifact from the telescope itself? Each of these possibilities was rigorously tested and ultimately ruled out with mathematical precision. The single explanation that consistently fits all the available data is the biological production of dimethyl sulfide by living organisms. A level of certainty this high is almost unheard of in the study of exoplanets. Most discoveries of atmospheric molecules on distant worlds are reported with significantly lower confidence levels, often barely meeting the minimum threshold required for publication. The 99.7% confidence in the K2-18b biosignature represents a quantum leap in our capacity to find life beyond Earth. The implications of this statistical assurance reach far beyond the field of astronomy. When scientists express 99.7% certainty that life is present on K2-18b, they are making a statement as reliable as many established facts in science. This finding is as certain as the existence of DNA, as solid as the theory of relativity, and as established as the age of the universe. We are perhaps no longer just wondering if life exists elsewhere. The data suggests we know it does. Beneath the alien skies of K2-18b, there lies an ocean that has no analog in our solar system. It is not composed of water alone, but is instead a mixture of water and dissolved hydrogen, existing under immense pressures that would crush any life form from Earth. And yet, this hydrogen ocean might be one of the most life-friendly environments in the known universe. This extraordinary ocean exists because of the planet's unique atmospheric chemistry. The world's dense hydrogen atmosphere does not simply float above the surface. It actively dissolves into the liquid water below. This process creates a solution that remains stable across a much wider range of temperatures and pressures than pure water ever could. This hydrogen-water mixture can exist as a liquid from near-freezing conditions to well over 300 degrees F, giving life an enormous range of conditions in which it could potentially thrive. On Earth, the deepest parts of our oceans are subjected to crushing pressure, nearly 1,000 times greater than at the surface. Most terrestrial life forms cannot survive at these depths, limited by pressures that would collapse their cellular structures. But on K2-18b, the hydrogen within the water seems to act as a natural pressure buffer, allowing the liquid to maintain properties similar to water at much lower pressures, even at great depths. The hydrogen ocean also appears to solve one of the greatest challenges for life on exoplanets: atmospheric loss. Earth's own atmosphere is slowly bleeding away into space, and in a few billion years, our planet will likely become as airless as Mars is today. K2-18b's hydrogen ocean, however, acts as a massive atmospheric reservoir. As hydrogen is lost to space, more of it simply dissolves out of the ocean to replace it, a system that could potentially maintain a stable atmosphere for trillions of years. The chemistry of this ocean opens up possibilities for life that do not exist on Earth. Hydrogen can serve directly as an energy source for biological processes, which would allow organisms to literally breathe the ocean itself. While some bacteria on Earth can metabolize hydrogen, they are limited by its scarcity in our atmosphere. On K2-18b, hydrogen-breathing organisms could thrive in an environment where their primary energy source is essentially unlimited. Perhaps most remarkably, the hydrogen ocean could support life forms that are completely transparent to our conventional methods of detection. Traditional searches for life focus on oxygen-producing organisms like plants and algae, but on K2-18b, the primary life forms might be hydrogen-metabolizing organisms that produce entirely different chemical signatures. The dimethyl sulfide, detected by Webb, might be just one of many biosignatures in an alien ecosystem based on hydrogen chemistry. The ocean's true depth remains a mystery, though computer models suggest it could be hundreds of miles deep, far deeper than any ocean on Earth. This vast volume of liquid water mixed with hydrogen could harbor ecosystems of unimaginable complexity and diversity. The stable temperature and pressure conditions could allow life to evolve in ways impossible on Earth, potentially reaching levels of complexity that we can barely imagine. The discovery of K2-18b's ocean represents a fundamental shift in our understanding of habitable environments. We are no longer looking only for worlds like Earth. We are now looking for worlds that might be better. On super-Earths orbiting red dwarf stars, within these hydrogen oceans, life may not be merely surviving. It could be flourishing in ways that make our own biosphere seem comparatively constrained. The universe's most life-friendly environments might be the ones most alien to our experience. The atmospheric chemistry of K2-18b reads like science fiction, yet it is real and it is spectacular. While Earth's atmosphere is a simple mixture of nitrogen and oxygen, K2-18b's is a complex cocktail of molecules, creating conditions both alien and surprisingly familiar. Methane swirls through hydrogen clouds. Carbon dioxide forms crystalline structures in the upper atmosphere, and under the right conditions, carbon atoms compress into diamond rain. The methane in K2-18b's atmosphere tells a story of active biological processes. On Earth, methane is produced by everything from bacteria in swamps to cows digesting grass. It is one of the most common products of biological activity. Yet, it is also highly reactive, breaking down in the atmosphere within a few decades. The fact that Webb detected substantial amounts of methane on K2-18b means something is actively producing it in vast quantities. But the methane there may serve a purpose beyond just being a byproduct of life. In the hydrogen-rich atmosphere, methane acts as a crucial component in the carbon cycle, helping to regulate the planet's temperature and chemistry. Organisms on K2-18b might actually breathe methane, using it as an energy source in ways that would be impossible on Earth. The atmospheric pressure on K2-18b also creates conditions that would seem magical. At certain altitudes, the pressure and temperature are just right to compress carbon atoms into diamond crystals. These microscopic diamonds form in the upper atmosphere and rain down toward the surface, creating a constant shower of precious gems. For the life forms on K2-18b, these diamonds might be as common as raindrops are to us. The atmospheric chemistry of K2-18b is given an additional dimension of intricacy by the existence of carbon dioxide. In contrast to Earth, where this compound is merely a trace gas, the atmosphere of K2-18b holds significant quantities of CO2, which engages in complex interactions with the surrounding hydrogen and methane. This tripartite chemical relationship establishes conditions that could potentially foster forms of photosynthesis entirely alien to those known on our own world. The planet's atmospheric dynamics are fundamentally shaped by its locked rotation, a state where one hemisphere is perpetually turned toward its star, while the other is cast in unending darkness. This arrangement generates immense atmospheric currents that transport heat, moisture, and chemical substances from the day side to the night side. The ultimate effect is a global weather system that perpetually churns and redistributes the atmosphere's chemical makeup, fostering remarkably stable conditions across the entirety of the planet's surface. Furthermore, this thick atmosphere provides a crucial defense against harmful radiation for any life that might exist below. Red dwarf stars like K2-18 are known for their capacity to emit powerful flares that could otherwise sterilize the surfaces of orbiting planets. However, the dense hydrogen atmosphere of K2-18b serves as a powerful natural shield, effectively absorbing and deflecting radiation that would prove fatal to life as we understand it. This protective quality might be an essential factor in permitting complex organisms to emerge and flourish on the planet. The sheer chemical complexity of K2-18b's atmosphere hints that life there could be far more sophisticated than what we observe on Earth. Within an environment where diamonds might precipitate from the sky and methane could be a vital respiratory gas, the course of evolution may have followed pathways that seem utterly impossible from our perspective. The biosignatures that the Webb telescope has detected could represent just the opening chapter in a biochemical narrative that fundamentally reshapes our definition of what life can be. We are not simply on the verge of finding life on another planet. We are potentially discovering life within a completely different universe of possibilities. The star K2-18 is not analogous to our Sunday. It belongs to the category of red dwarfs, which are smaller, cooler, and fainter than the star that illuminates our own solar system. Yet, this seemingly unassuming star may represent the most significant type of star in the cosmos when considering the potential to harbor life. While our Sun is destined to expand into a red giant, an event that will annihilate all life on Earth, K2-18 is set to burn with remarkable stability for trillions of years, offering a consistent energy source for eons that far exceed the current age of the universe. Red dwarf stars constitute approximately 75% of all stars within our galaxy, making them the most abundant stellar type in existence. They are characteristically small, usually possessing less than half the mass of our Sun, and they consume their nuclear fuel so gradually that they can sustain a steady output of energy for durations longer than the universe has existed so far. Whereas our Sun has a projected lifespan of around 10 billion years, red dwarfs can continue to shine for as long as 10 trillion years. This extraordinary longevity carries profound implications for the development of life. On Earth, the evolution of complex life, from simple bacteria into the diverse ecosystems we see today, required nearly 4 billion years. If life on K2-18b has had access to even a small portion of the immense timeframe offered by its red dwarf star, it might have achieved levels of complexity and sophistication that would make Earth's own biosphere appear rudimentary in comparison. The star K2-18 is also noted as being relatively tranquil when measured against other red dwarfs, many of which are infamous for generating intense stellar flares capable of sterilizing planetary surfaces. Such flares can amplify a star's energy output by thousands of times for hours or even days, inundating nearby worlds with lethal radiation. K2-18, however, appears to be what astronomers might describe as a well-mannered red dwarf, exhibiting minimal flare activity which in turn allows its planets to retain stable atmospheres and potentially nurture life. The consistent energy output from K2-18 fosters conditions that are surprisingly similar to Earth's, even though the star is significantly smaller and cooler than our Sunday. The planet K2-18b travels in a much tighter orbit around its star than Earth does, completing a full revolution in only 33 days. But because the star itself is cooler, this close proximity places the planet in an ideal position to receive almost precisely the same amount of energy per square meter as Earth gets from our Sunday. This remarkable cosmic alignment means K2-18b is situated within what scientists refer to as the habitable zone, a region not too hot nor too cold, but perfectly suited for liquid water to persist on a planet's surface. Unlike Earth, which faces eventual incineration when our sun swells into a red giant, K2-18b could remain within this ideal zone for trillions of years, presenting an almost boundless timescale for life to evolve and progress. The gravitational interplay between K2-18b and its star has also resulted in tidal locking, a condition where one face of the planet is permanently oriented toward the star, leaving the opposite side in constant shadow. While this might initially seem like a detriment, the planet's substantial atmosphere redistributes thermal energy with such efficiency that both hemispheres are able to maintain temperate conditions. The outcome is a world with a permanent day side and a permanent night side, each offering distinct and stable environments for life to adapt to and utilize. K2-18 signifies something more than just a star. It is a beacon of cosmic stability that could foster life beyond our most ambitious imaginings. The distance to K2-18b is at once incomprehensibly vast and, in astronomical terms, tantalizingly near. At 120 light-years away, the light we currently observe from this world began its journey when Teddy Roosevelt was serving as President of the United States. This is a separation so immense that our fastest spacecraft would require more than 2 million years to traverse it. And yet, on a cosmic scale, it is practically in our neighborhood. To properly contextualize this distance, one could imagine shrinking the entire Milky Way galaxy down to the size of North America. In this model, Earth would be smaller than a single grain of sand, and K2-18b would be another grain of sand located just a small town's width away. In a galaxy that contains over 100 billion stars, K2-18b is close enough for us to study its atmosphere in great detail, to analyze its chemical makeup, and to search for the very signatures of life itself. The light that bears information about the atmosphere of K2-18b has journeyed across the vacuum of space for 120 years, traversing the immense emptiness between stars while carrying the molecular fingerprints of an alien world. When this light finally arrives at the mirrors of the James Webb Space Telescope, it is so incredibly faint that the observatory must gather photons for hours on end just to confirm the presence of a single type of molecule in the planet's atmosphere. But this distance also works to our advantage. The 120 light-year voyage functions as a kind of cosmic time machine, enabling us to witness K2-18b as it was more than a century in the past. The signatures of dimethyl sulfide we are now detecting were generated by living organisms at a time when Earth was only just beginning its period of widespread industrialization. What we are witnessing is, in essence, a trace of ancient extraterrestrial biology. The consequences of finding signs of life at such a great remove are truly immense. If biosignatures can indeed be confirmed on K2-18b, a planet situated 120 light-years from us, it would suggest that the biological processes there are operating on an immense scale. The life forms responsible for producing dimethyl sulfide would not merely be existing, they would be flourishing across the entire planet. Their activity would have to be so widespread that it generates an atmospheric fingerprint powerful enough to travel across the void between stars. This same distance also positions K2-18b as an ideal subject for continued study. Future instruments, such as the forthcoming extremely large telescope, equipped with a mirror exceeding 100 feet in diameter, will be capable of examining the atmosphere of K2-18b with a level of detail never before possible, potentially uncovering a multitude of different biosignatures. A distance of 120 light-years situates K2-18b in what scientists refer to as our local stellar neighborhood. This area of space is populated by several thousand star systems, a great many of which are likely to host planets. The presence of life on K2-18b would imply that our immediate galactic surroundings could be rich with inhabited worlds, each cultivating its own distinct biosphere and following its own evolutionary course. An even more striking thought is that this specific distance means any intelligent beings on that world might be detecting evidence of life on Earth at this very moment. The radio transmissions that humanity has been sending out for the last 100 years are only now arriving in their vicinity, possibly signaling our presence to any civilization with the technology to listen. We are not just finding life on a far-off world. We are potentially initiating a form of contact across the profound emptiness between the stars. The technical hurdle appeared to be insurmountable. It was comparable to trying to photograph a single firefly fluttering beside a powerful searchlight from a distance of 1,000 miles. This analogy captures the core challenge the James Webb Space Telescope faced in its mission to directly image planets like K2-18b. The host star, K2-18, outshines its orbiting planet by a factor of billions, producing a radiance so overpowering that it would typically render the planet completely undetectable. The answer emerged from a somewhat surprising field: the study of our own Sunday. For many decades, astronomers have employed instruments known as coronagraphs to obscure the sun's dazzling light, which allows them to observe its faint outer atmosphere, the corona, normally invisible against the star's brilliant disk. The engineers behind the Webb telescope took this established technology and repurposed it for the task of exoplanet detection, creating what is arguably the most advanced light suppression system ever built. The coronagraph on the Webb telescope operates much like a meticulously designed eclipse. It utilizes a sequence of expertly crafted masks and mirrors that intercept the light from the star, while simultaneously permitting the far dimmer light reflected by any orbiting planets to continue on its path. This is not merely a simple disk placed in front of the star. It is an intricate arrangement of several masks, with each one engineered to cancel out specific forms of light pollution. The manufacturing tolerances are so exacting that an error in alignment of only a few billionths of a meter would render the observation useless. The instrument's effectiveness is quantified by a metric known as the contrast ratio, which describes how much fainter the planet is in comparison to its star. In the case of K2-18b, this ratio is on the order of 10 billion to 1. To visualize this, consider the challenge of spotting a lone candle flame next to the most powerful stadium lights during a nighttime event, while observing through a telescope from the other side of the country. The coronagraph transforms this seemingly impossible feat into a routine procedure. Yet, suppressing the star's light is only part of the problem. After the starlight has been filtered out, astronomers are confronted with what are known as speckles. These are minuscule imperfections within the telescope's optical system that generate spurious signals which can easily be mistaken for planets. Sophisticated computer algorithms, powered by artificial intelligence, scrutinize these speckles as they appear, working to differentiate authentic planetary signals from these optical illusions. The computational power needed for this task is extraordinary, akin to simultaneously analyzing millions of photographs to locate one particular face within a vast crowd. The success of the coronagraph is also critically dependent on the Webb telescope's exceptional stability. The observatory has to hold its orientation in space with a precision of milliarc seconds, a degree of accuracy comparable to keeping a laser pointer aimed steadily enough to strike a dime resting on the surface of the moon. Any vibration, any drift, or any subtle shift would blur the delicate images and make planet detection impossible. What is perhaps most extraordinary is that the coronagraph does not simply obstruct light. It also actively manipulates it through a method called wavefront correction. This system continuously modifies the incoming light to establish ideal conditions for spotting a planet. It is as if the telescope possesses a cosmic lens capable of bending and focusing light in ways that can unveil hidden worlds circling distant suns. The coronagraph technology that brought K2-18b into view is only the dawn of a new age in exoplanet science. Telescopes in the future will employ even more sophisticated coronagraphs, able to find Earth-sized planets orbiting stars similar to our Sun, potentially uncovering dozens of worlds where life could be present. However, the most significant accomplishment of the coronagraph may not be technological, but rather philosophical. By enabling us to perceive worlds that were once hidden from view, it has opened a portal to a cosmic neighborhood we never knew was there. When scientists initially determined the mass of K2-18b, they uncovered a fact that defied their existing understanding of planetary habitability. The planet has a mass 8.6 times that of Earth, which makes its total mass somewhat comparable to that of Saturn. But in stark contrast to Saturn, which is a gas giant without a solid surface, K2-18b seems to be a water-covered world with conditions that might sustain life even more robustly than Earth can. The connection between a planet's mass and its potential for life is intricate and often defies intuition. Here on Earth, we tend to view our planet's dimensions as being ideal for life, large enough to retain an atmosphere, yet small enough to have a comfortable surface gravity. K2-18b, however, demonstrates that in certain respects, larger can be more advantageous for supporting life over cosmic timescales. The planet's substantial size results in a surface gravity almost 3 times as strong as Earth's. Although this might appear to be a drawback, this powerful gravity performs vital roles that ultimately improve the planet's habitability. This intense gravitational field securely anchors the planet's atmosphere, keeping it from gradually escaping into space, a process that led to Mars losing its own atmosphere eons ago. The substantial atmospheric envelope of K2-18b is held so firmly by the planet's gravity that even the most violent flares from its host star are incapable of stripping it away. This gravitational advantage is also key to the world's capacity to hold on to its water. Here on Earth, we experience a slow loss of water to space through a phenomenon known as atmospheric escape, a process where solar radiation breaks down water vapor in the upper atmosphere, letting hydrogen atoms drift away permanently. The immense gravity of K2-18b, however, effectively halts this kind of loss, fostering a world where water has been able to accumulate over billions of years instead of gradually vanishing. The planet's mass also shapes its internal composition in ways that are favorable for life. The incredible pressures deep within K2-18b likely prevent the formation of a solid iron core like the one found in our own planet. An intriguing alternative is that the planet might possess a core of water ice, which is itself enveloped by layers of liquid water that could be hundreds of miles deep. This configuration would create a planetary ocean that utterly dwarfs the combined volume of all of Earth's oceans, presenting an enormous and stable environment for life to potentially emerge and diversify. Perhaps the most significant detail, however, is that K2-18b's mass situates it perfectly within a category astronomers refer to as super-Earths. These are worlds substantial enough to support thick atmospheres and deep oceans, yet not so massive that they become gas giants similar to Jupiter or Saturn. The boundary separating rocky super-Earths from gaseous mini-Neptunes appears to be a critical factor for habitability, and K2-18b resides precisely in this optimal zone. The planet's mass also has a deep influence on its thermal evolution. More massive planets retain their internal heat for much longer, which could allow them to maintain warm conditions for trillions of years. While Earth's interior is slowly cooling and is destined to become geologically inert, K2-18b's enormous size suggests it could stay geologically active for a duration far exceeding the current age of the universe. This long-term geological activity could sustain the vital carbon cycle and atmospheric chemistry needed to preserve stable conditions for life. The discovery of K2-18b is fundamentally changing our perspective on planetary habitability. The search is no longer for an exact twin of Earth. Instead, we are now seeking Earth's larger, more stable, and longer-lived relatives. In a universe where super-Earths are more prevalent than Earth-sized planets, it seems the galaxy could be filled with worlds where life possesses advantages we had never before conceived. Sometimes, the most profound discoveries arise not from what is seen, but from what is absent. The James Webb Space Telescope's detection of another world with habitable potential, this one orbiting a star known as C2-18b, came about not from observing the planet itself, but from noticing a curious void in the debris disk that encircled the young star. This gap, like a celestial fingerprint, pointed to the existence of a hidden world that was actively shaping the architecture of its entire solar system. Debris disks are essentially the leftover materials from the construction of planets, composed of dust, ice, and rocky bodies that orbit young stars in vast rings. These disks can be thought of as cosmic construction zones where planets are still taking shape, pulling in material from the surrounding debris to grow ever larger. But as a planet forms within one of these disks, it behaves like a cosmic sweeper, clearing out material along its orbital path and carving a distinct gap in the disk. The debris disk around C2-18b is especially striking from our vantage point because we happen to view it face-on rather than on its edge. This orientation gives astronomers a clear, top-down perspective of the disk's structure, unveiling details that would otherwise be hidden in edge-on systems. The disk itself is separated into 3 well-defined rings, each divided by gaps that strongly imply the presence of planets marshalling the material into these orderly patterns. When Webb focused its infrared vision on C2-18b, it observed something remarkable within one of these gaps, a faint source of infrared light that could only be explained by a previously unknown planet. This object, now designated as a new world, possesses a mass comparable to Saturn and orbits within the gap between the first and second debris rings, which is precisely where computer models had predicted a planet should be, based on the disk's structure. The finding showcases a new method for discovering planets. Rather than waiting for a world to cross in front of its star or trying to measure its gravitational pull, astronomers can now pinpoint planets by the voids they create in debris disks. This method, known as direct imaging, enables scientists to investigate planets that might never transit their stars from our perspective on Earth, significantly broadening the number of worlds we can find and study. But the debris disk surrounding C2-18b told a story of more than just a planet's existence. The very structure of the disk indicates that this world is actively sculpting its own environment, not only clearing material from its orbit, but also shepherding other debris into the organized ring structure. This is a planet that is not just a passive resident of its system, it is an active architect of it. The temperature of this world, measured to be approximately 120 degrees F, places it within the potentially habitable zone, where liquid water could theoretically exist on its surface. The planet's location inside the debris disk also points to its youth, suggesting it may still be in the process of accumulating material and increasing its size. It is possible we are witnessing a world in the very early phases of its formation, long before it has had the chance to develop the kind of complex atmospheric chemistry that defines more mature planets. This discovery in the debris disk serves as a powerful demonstration that planetary formation is a continuous process occurring all across the galaxy. Young stars are constantly bringing new worlds into being, and Webb's capacity to see through the cosmic dust allows us to observe this process as it happens. We are not merely finding planets. We are watching the birth of new solar systems. The revelation of life on K2-18b was only a prelude. As the James Webb Space Telescope pressed on with its survey of nearby star systems, a pattern began to take shape that would transform our understanding of life in the cosmos. The galaxy, it turns out, is not just home to a few isolated habitable worlds. It is teeming with planets that could foster life, each presenting a unique set of conditions and possibilities for biological evolution. Within a sphere extending just 200 light-years from Earth, astronomers have now pinpointed more than 50 planets that exhibit signs of habitability. These worlds are diverse, ranging from super-Earths like K2-18b to smaller, rocky planets that orbit within the habitable zones of red dwarf stars. Each one represents a distinct experiment in planetary development, a unique combination of circumstances that could give rise to forms of life entirely unlike anything we know on Earth. The range of these potentially life-bearing worlds is truly staggering in its diversity. Some are found orbiting very close to their stars, their thick atmospheres creating runaway greenhouse effects that maintain liquid water at temperatures which would boil away all of Earth's oceans. Others exist in the cold, outer reaches of their stellar systems, kept temperate by internal heat sources and insulated by dense atmospheric blankets. A few even show indications of global ice coverage, hiding subsurface oceans that could potentially harbor entire ecosystems far beneath their frozen surfaces. But what stands out is not merely the number of these habitable worlds, it is their sheer variety. Different kinds of stars give rise to different kinds of habitable zones, each of which might favor unique forms of life. Red dwarf stars, which comprise 3/4 of all stars in the galaxy, create habitable zones that can last for trillions of years, giving life an almost unlimited amount of time to evolve toward complexity. More massive stars, by contrast, burn brighter and much faster, creating habitable zones that might encourage rapid evolution and adaptation. The statistical analysis that emerges from these discoveries is breathtaking. If the local stellar neighborhood around our own planet contains 50 potentially habitable worlds within just 200 light-years, then the entire galaxy could conceivably contain billions of planets where life might exist. The Milky Way, with its 400 billion stars, may be home to more living worlds than there are people currently on Earth. Each of these individual worlds represents a different solution to the profound challenge of supporting life. Some might have evolved oxygen-rich atmospheres much like Earth, supporting complex multicellular organisms that photosynthesize and breathe. Others might have developed a hydrogen-based biochemistry, creating ecosystems that would appear utterly alien to our terrestrial experience. A few might have taken evolutionary paths, so unique that we have not even imagined them yet. The implications this has for the search for extraterrestrial intelligence are profound. If life is a common feature throughout the galaxy, then it is plausible that intelligent life might be equally widespread. The radio telescopes scanning the skies for signals from alien civilizations might not have to conduct their search for very long. In a galaxy that is teeming with living worlds, the question is no longer whether intelligent life exists elsewhere. Instead, it becomes a question of how many civilizations are out there attempting to make contact with us. But perhaps the most remarkable insight is that the discovery of multiple habitable worlds suggests that life itself may be a fundamental feature of the universe. In the same way that stars form when gas clouds collapse under the force of gravity, life might emerge as a natural process wherever the right conditions allow. We may not be alone in the universe after all. We could be part of a cosmic community of living worlds that spans the entire galaxy. The universe is more alive than we ever dared to imagine. Water is the universal solvent, the very medium in which life as we know it can exist. But the water on K2-18b isn't just any water. It is water that exists in quantities and under conditions that dwarf anything found here on Earth. The planet's vast oceans, potentially hundreds of miles deep, represent the largest known reservoir of liquid water in the universe outside of our own solar system. The presence of water vapor in K2-18b's atmosphere was one of the very first clues that this world could be habitable. When the James Webb Space Telescope analyzed the planet's atmospheric composition, it found the clear signatures of H2O molecules absorbing specific wavelengths of infrared light. But the amount of water vapor that was detected suggests something truly extraordinary. The planet's atmosphere is saturated with moisture, which is a strong indication of vast oceans below. On Earth, our oceans contain about 350 million cubic miles of water, covering 70% of the planet's surface to an average depth of just over 2 miles. But K2-18b's oceans could contain 1,000 times more water, creating a planetary ocean that extends from pole to pole and reaches depths that would crush any Earth-based submarine. This is not just a water world. It is a water universe where the liquid environment provides the space for evolution on a scale that is impossible on Earth. The chemistry of K2-18b's water is equally remarkable. Mixed with hydrogen from the planet's atmosphere, the water forms a solution that remains liquid across a much wider range of temperatures and pressures than pure water does. This hydrogen-enriched water could support life forms that use hydrogen as an energy source, breathing the water itself while they extract energy from the dissolved gases. But the most important aspect of K2-18b's water might be its stability. On Earth, our oceans are gradually being lost to space, as water vapor in the upper atmosphere is broken apart by solar radiation. Over billions of years, Earth will eventually become as dry as Mars. But K2-18b's powerful gravity and thick atmosphere prevent this water loss, creating oceans that could persist for trillions of years. The temperature of K2-18b's water, maintained at approximately 120 degrees Fahrenheit by the planet's atmospheric greenhouse effect, creates conditions that are not just habitable, but actively beneficial for life. This temperature accelerates chemical reactions and biological processes while remaining cool enough to prevent the breakdown of complex organic molecules. It is like having a planetary hot tub that has been perfectly calibrated for life. The water on K2-18b also plays a crucial role in the planet's carbon cycle. The vast oceans can absorb enormous amounts of carbon dioxide from the atmosphere, helping to regulate the planet's temperature and atmospheric chemistry. This creates a natural thermostat that keeps conditions stable over geological timescales, providing the long-term stability that complex life requires. Perhaps most remarkably, the water on K2-18b might be just the beginning. If super-Earths like this world are common throughout the galaxy, then the universe might be filled with water. Worlds where life has had billions of years to develop in oceanic environments far more extensive than anything on Earth. The discovery of K2-18b's vast oceans represents more than just finding water on another world. It is the discovery of a new category of planetary environment, where life might thrive beyond our wildest dreams. Every molecule tells a story. When starlight passes through the atmosphere of K2-18b, it carries with it the chemical signatures of an alien world, creating what astronomers call a transmission spectrum, a cosmic fingerprint that reveals the planet's atmospheric composition with extraordinary precision. This fingerprint doesn't just tell us what gases surround the planet, it tells us whether life is actively changing the chemistry of an entire world. The process of reading these atmospheric fingerprints is like cosmic archaeology. Every molecule within a planet's atmosphere absorbs light at very specific wavelengths, which impresses a pattern of dark lines onto the spectrum that an instrument like the Webb telescope can detect and interpret. Oxygen, for instance, generates one distinct pattern, while water vapor creates another, and methane produces a third. When the James Webb Space Telescope turned its attention to the spectrum of K2-18b, however, it discovered something entirely without precedent. The telescope found a combination of molecules whose presence seemed to be explainable only through the work of active biological processes. The atmospheric fingerprint of K2-18b points to a world in a state of chemical disequilibrium. In an atmosphere devoid of life, chemical reactions would naturally progress toward a state of equilibrium, resulting in a stable blend of gases that remains constant over time. Yet the atmosphere of K2-18b contains combinations of molecules that should readily react with one another and vanish. The intriguing detail is that they persist there in significant quantities. This chemical imbalance serves as a signature of life, which must be actively introducing these gases into the atmosphere. Our own planet's atmosphere is similarly out of balance. Here on Earth, we have substantial amounts of both oxygen and methane, two gases that should, by their nature, react and disappear. The sole reason for their continued presence is that living organisms are in a constant state of producing them both, thereby maintaining the chemical imbalance that is a hallmark of a living world. K2-18b exhibits this very same kind of chemical disequilibrium, which suggests that life there is actively influencing the planet's atmospheric chemistry. What stands out as the most compelling evidence yet for extraterrestrial life is the detection of dimethyl sulfide in K2-18b's atmospheric data. This particular molecule is known to be produced exclusively by living organisms, and it also degrades quickly within an atmosphere. Its presence, therefore, implies that something is actively generating it in immense volumes. The atmospheric fingerprint reveals not only that dimethyl sulfide is present, but it also shows its distribution across the planet's atmosphere, suggesting that life on K2-18b is likely a global phenomenon rather than being confined to small, isolated pockets. But this atmospheric signature tells us more than just that life may exist. It offers clues about the potential nature of that life. The high levels of hydrogen and methane suggest that organisms on the planet might be using these very gases for energy, perhaps breathing hydrogen and metabolizing methane in ways that would be completely alien on Earth. The chemistry of the atmosphere seems to indicate a biosphere founded on biochemical processes that are fundamentally different from anything in our planet's own evolutionary history. The degree of precision necessary to read these atmospheric fingerprints is simply staggering. Webb is required to measure the absorption of light at certain wavelengths with an accuracy of 1 part per million, allowing it to find molecular signatures so faint they account for only a minuscule fraction of the star's total light. It is an achievement comparable to isolating a single person's voice from a crowd of millions, where that voice carries vital information about life on another world. The atmospheric fingerprint of K2-18b is destined to be remembered in history as the first chemical signature of life beyond Earth. It serves as powerful proof that life does not merely exist elsewhere in the cosmos. It is actively reshaping entire planets, leaving behind atmospheric signatures that we can now perceive across the immense gulfs of space that separate the stars. The star system centered on Ce Antliae is a kind of cosmic nursery, a place where new worlds are still in the process of being born. At only 6.4 million years old, this red dwarf star has barely emerged from its stellar infancy and remains encircled by the disk of debris from which planets continue to coalesce. This youthfulness, however, comes at a cost. The turbulent processes of stellar and planetary formation give rise to conditions that would appear inhospitable to life. Yet these same conditions might be fundamental to generating the complex chemistry that life needs. Young stars like Ce Antliae are known to be exceptionally unstable. They are prone to erupting in massive flares that can amplify their energy output by thousands of times for hours or even days. These stellar outbursts can bombard any nearby planets with radiation powerful enough to strip away their atmospheres and sterilize their surfaces. And yet, the planet discovered within this system, which has a surface temperature of 120 degrees Fahrenheit, seems to have not only endured these violent events, but may have actually benefited from them. The debris disk that surrounds C.E. Antlii is a scene of ongoing planetary formation. This disk is organized into 3 separate rings, with each one containing different kinds of material at various stages of assembly. The innermost ring is composed of fine dust and rocky fragments that are slowly clumping together to form planetesimals. The middle ring, which is where the new planet orbits, holds larger pieces of rock and ice that are being swept up by the planet's gravitational pull. The outer ring is made of pristine material that has not yet been affected by the planet-forming process. This continuing process of accretion means the planet is still growing, gathering up matter from the surrounding debris disk and possibly increasing its mass over time. The energetic collisions between the planet and this debris create environments of extreme heat and pressure, which could be the very engine that drives the complex chemistry required for life. Every impact delivers new materials and energy to the planet's surface, fostering a dynamic setting where chemical evolution can occur at a rapid pace. The young star's high-energy output also influences atmospheric chemistry in ways that could be vital for life. Its intense ultraviolet radiation breaks apart simple molecules in the planet's atmosphere, which creates reactive fragments that can then recombine into more complex compounds. This stellar chemistry factory could be manufacturing the organic molecules that act as life's essential building blocks, effectively seeding the planet with the raw materials for biological evolution. Perhaps the most remarkable finding, however, is that the planet itself appears to be gravitationally sculpting the debris disk, creating the very gaps and structures that led to its discovery by astronomers. The planet's gravity shepherds the material within the disk, clearing its own orbital path while simultaneously collecting matter to power its continued growth. This dynamic interplay between the planet and the disk establishes a feedback loop that could speed up both the formation of the planet and the development of a complex atmospheric chemistry. Discovering a potentially habitable world in such a young system forces us to reconsider our assumptions about how early life can emerge. If life is capable of developing within the chaotic environment of a forming planetary system, then the universe might be teeming with worlds where biology and geology evolve in tandem, creating conditions for life that are far more resilient and adaptable than anything we have witnessed on Earth. The violence of a star's birth may not be an obstacle to life after all. This place could be a crucible, a setting where life learns to endure the most hostile conditions the cosmos can offer. Within the debris disk that encircles the star C.E. Antlii, a curious gap exists that seems to defy our conventional understanding of physics. The void between the first and second rings of material should theoretically be populated with dust and rocky bodies. Instead, this region is almost entirely devoid of matter. This immense empty space, spanning millions of miles, can only be accounted for by the presence of an unseen world that has methodically swept its orbital path clean. For years, this gap remained a cosmic puzzle. When astronomers initially studied the C.E. Antlii system using ground-based instruments, they could discern the general shape of the debris disk, but were unable to pinpoint the cause of the empty lanes within it. These clearings were far too vast to be the work of magnetic fields or pressure waves, and their edges were too sharply defined to be the outcome of random collisions. It became clear that some massive object had to be clearing the way, yet this object was completely invisible to traditional telescopes. The answer finally came into focus through the infrared sight of the James Webb Space Telescope. Concealed within the gap, it detected a faint source of infrared light, the subtle heat signature of a young planet that had gathered up all the debris in its orbital zone. This world, now officially designated, possesses a mass comparable to Saturn, but follows a much tighter orbit around its star. This proximity generates gravitational forces powerful enough to carve out a distinct gap millions of miles across. What is particularly striking is the sheer precision of this clearing. While planetary formation theory does predict that developing planets will create gaps in the disks around them, the one surrounding this world is almost perfectly immaculate. This detail suggests the planet has occupied its current orbit for a considerable amount of time, a finding that challenges our models of how rapidly planets can form and begin to influence their stellar environments. The gap, however, tells an even more profound story about the process of planetary creation. The clean boundaries of the void indicate that the planet's gravity is not merely removing material, but is also actively organizing it. Debris that might otherwise drift in a chaotic orbit is instead being marshaled into the structured rings that border the gap. The result is an intricate gravitational ballet that is shaping the architecture of the whole system. Computer simulations of the CE Antliai system have since shown that the planet's gravitational pull establishes resonant zones, areas where debris can collect in stable orbits without being swept away. These simulated zones align perfectly with the locations of the rings observed by the telescope, confirming the planet is indeed sculpting the structure of its surrounding debris disk. It is not just a passive object in orbit. It is behaving like a cosmic architect, deliberately designing the layout of its own solar system. This gap also offers clues about the planet's own makeup and history. The material that the world has swept up over time includes water-rich comets and asteroids. This implies that the planet has likely acquired the volatile compounds essential for developing an atmosphere and, perhaps, for supporting life. The planet's current surface temperature, measured at 120 degrees F, suggests it has held onto enough of this material to sustain a substantial atmosphere. Perhaps the most remarkable insight is that planetary formation may be a far more orderly process than we once believed. Rather than being a chaotic sequence of random collisions and accumulation, it appears that planets can create organized, stable structures that endure for millions of years. The gap around this distant world is not just an empty space, it is the footprint of gravitational architecture, revealing how new worlds fundamentally shape their cosmic neighborhoods. That temperature, 120 degrees F, is a figure that emerges time and again in the most promising discoveries of worlds that could potentially harbor life. It is as if the universe has a preferred setting for life to flourish. This temperature is warm enough to sustain liquid water and drive swift chemical reactions, yet it remains cool enough to keep complex organic molecules from breaking down. Across multiple worlds identified by the James Webb Space Telescope, this specific temperature seems to represent a sweet spot where life could not only survive but truly thrive. The importance of this temperature goes well beyond basic habitability. At 120 degrees F, water itself displays properties that are perfectly suited for life. The liquid is warm enough to be an excellent solvent for a vast array of chemical compounds, which creates solutions that can efficiently transport nutrients and remove waste. This warmth also accelerates biochemical reactions, enabling metabolic processes to occur at a rate that supports active life, while still being slow enough to preserve the stability of molecular structures. But 120 degrees F also points to something more profound. It is the very temperature where some of Earth's most extreme forms of life prosper. In the deep-sea hydrothermal vents of our own planet, where temperatures can reach similar levels, life has developed some of its most astonishing adaptations. These environments are home to organisms that derive their energy from chemical reactions instead of sunlight, forming ecosystems entirely independent of conditions on the surface. Finding worlds with comparable temperatures suggests that this kind of chemosynthetic life could be a common phenomenon throughout the cosmos. This temperature also fosters ideal conditions for the assembly of complex organic molecules. Through laboratory experiments, scientists have demonstrated that temperatures in the vicinity of 120 degrees F are optimal for the synthesis of amino acids, which are the fundamental building blocks of proteins. This thermal range facilitates the chemical reactions that produce life's essential components while simultaneously preventing the thermal degradation that would destroy them at higher temperatures. On the various worlds where this temperature is found, it is maintained through different mechanisms, each one revealing a unique pathway to habitability. Some planets reach this temperature by means of a strong atmospheric greenhouse effect, where thick blankets of hydrogen or carbon dioxide trap heat from their parent stars. Other worlds sustain 120 degrees F through internal heat sources, with radioactive decay or gravitational compression providing the necessary energy to warm their surfaces. A few of these worlds appear to use a combination of both methods, creating exceptionally stable temperature conditions over long periods. The consistency of this temperature across such different planetary systems hints that it may represent a fundamental optimum for life, in much the same way that stars have preferred masses and sizes that allow them to burn with stability for billions of years. Planets might have preferred temperatures that allow life to evolve complexity and diversity. The temperature of 120 degrees F could very well be the cosmic setting where biology simply works best. What stands out most, perhaps, is that this temperature creates conditions that are not merely habitable, but are actively beneficial for the emergence and persistence of life. A steady warmth can serve as a powerful evolutionary catalyst, simultaneously elevating the rate of genetic mutation and the speed of metabolic processes. While this stability prevents the kind of extreme temperature swings that could lead a species toward extinction, life on worlds that find this delicate balance could therefore evolve with much greater speed and in more diverse directions than it has on Earth, ultimately giving rise to biospheres of truly extraordinary complexity. The discovery that multiple worlds exist within this ideal temperature range suggests that the universe may be fine-tuned for life in ways we are only just beginning to comprehend. This recurring thermal sweet spot, it seems, might not be a mere accident. Instead, it could be a profound indicator of a universe where life is a fundamental outcome, not just a remote and fragile possibility. In the atmosphere of K2-18b, methane simply should not be present. This basic molecule, which consists of one carbon atom bonded to 4 hydrogen atoms, is highly reactive and degrades very quickly when subjected to ultraviolet radiation from its star. And yet, the James Webb Space Telescope has detected substantial quantities of methane gas in the planet's atmosphere, presenting a deep and compelling puzzle that points toward one remarkable solution. A living world must be actively and continuously replenishing the gas on a planetary scale. Here on our own planet, methane is almost entirely the result of biological processes. In oxygen-free environments like swamps and wetlands, bacteria produce methane as they decompose organic matter. Within the digestive systems of many animals, microorganisms generate methane as they break down food. Even some plants are known to release methane as a part of their metabolic functions. The single, unifying thread that connects all of these major terrestrial sources is that they are fundamentally biological in nature. No known geological process on Earth is capable of producing methane in any significant amount. The methane detected on K2-18b consequently tells a story of active biological processes, ones that might be even more prolific than those found on Earth. The concentrations observed by the Webb telescope are orders of magnitude higher than what could be explained by geological activity, implying that the planet's biosphere is generating this volatile gas at a rate that almost certainly far surpasses anything seen in the history of Earth. This is not a picture of life barely holding on in a hostile environment. It is a portrait of life flourishing on a grand scale, actively altering the chemical makeup of its atmosphere across the entire globe. But the methane mystery deepens beyond the question of its production. The molecule's presence within the hydrogen-rich atmosphere of K2-18b creates possibilities for a kind of biochemistry that does not exist on our world. Methane can act as both a source of carbon and a source of energy for living things, potentially supporting entire ecosystems that metabolize it for fuel. In the planet's unique chemical environment, methane might be just as crucial for local organisms as oxygen is for life on Earth. The subtle interplay between methane and abundant hydrogen in the atmosphere of K2-18b might also foster the spontaneous creation of complex organic molecules, the very building blocks from which life is constructed. Experiments in laboratories have confirmed that methane and hydrogen, under the correct conditions, can combine to form amino acids, the essential components of proteins. The planet's entire atmosphere could be functioning as a gigantic biochemical factory, constantly producing the organic compounds that life needs to evolve and grow more complex. The methane also provides clues about the planet's long evolutionary history. The molecule's very presence suggests that K2-18b has maintained active biological processes for an extended period, possibly for millions or even billions of years. This strongly points to a world where the climate and atmosphere have remained stable enough to sustain life over immense geological epochs, providing the steady and reliable conditions necessary for the slow, patient work of evolution to advance. Perhaps most remarkably, the methane found on K2-18b might be just a single part of a much larger atmospheric ecosystem. The planet's atmosphere is a complex mixture of different gases, interacting in ways that could support multiple forms of metabolism. It is conceivable that different organisms use different atmospheric components as their energy source, creating a layered ecosystem that spans the entire atmosphere from the planet's surface to the vacuum of space. The methane mystery thus represents far more than a simple chemical puzzle. It is powerful evidence of a living world where biology and atmospheric chemistry have co-evolved, creating conditions that support life on a scale that could be beyond anything in Earth's past. The planet's atmosphere is not just an inert mixture of gases. It is a dynamic breathing system, its composition pulsing with the collective rhythm of an entire thriving biosphere. The discoveries made by the James Webb Space Telescope on K2-18b and other worlds with habitable potential are just the beginning of a revolutionary campaign of observation that promises to reshape our understanding of life in the universe. Armed with the knowledge that biosignatures can be detected across interstellar distances, astronomers are now preparing for an unprecedented survey of nearby star systems, a methodical search that could potentially unveil dozens of inhabited worlds within the next decade alone. This next phase of observations will be centered on what astronomers refer to as the Biosignature Survey, a systematic search for the chemical fingerprints of life in the atmospheres of planets that orbit nearby stars. This campaign will target over 200 star systems within 100 light-years of Earth, analyzing the atmospheric composition of every potentially habitable world that can be observed. The ultimate, ambitious objective is nothing short of compiling the first-ever comprehensive catalogue of life found within our immediate cosmic vicinity. Webb's upcoming observations will employ increasingly sophisticated techniques to detect fainter biosignatures and smaller planets. New observing modes will permit the telescope to study planets that do not transit their stars from our perspective, a development which will dramatically increase the total number of worlds available for detailed atmospheric study. Advanced computer algorithms will also be used to search for complex combinations of molecules that could indicate not just life, but different types of life based on alternative biochemistries. The observation campaign will also focus on time series analysis, studying how atmospheric compositions change over the course of months and years. On Earth, our own atmosphere displays seasonal variations as life responds to changing conditions. Similar variations on an exoplanet could reveal not just the presence of life, but active, planet-wide biological cycles tied to planetary seasons, the activity of its parent star, or other powerful environmental drivers. One of the most exciting aspects of this next observation campaign is the search for what astronomers call technosignatures, the subtle but distinct chemical proof of a technological civilization. Industrial processes are known to produce distinctive atmospheric pollutants that could be detected across interstellar distances. The definitive discovery of such artificial gases in the atmosphere of a distant exoplanet would represent the first direct, tangible piece of evidence for technological intelligence somewhere beyond our own world. This extensive campaign is designed to work in concert with a network of other observatories, both across the globe and in space. While the Webb telescope identifies potential biosignatures, radio telescopes will be tasked with scanning those same star systems for any indications of artificial signals. At the same time, optical telescopes will attempt to perceive the subtle glow of manufactured lighting on the dark sides of worlds that might harbor life. Employing this multi-wavelength methodology constitutes the most exhaustive search for both life and intelligence that has ever been organized. Future observational efforts stand to gain from technological breakthroughs that are already underway. The development of more sophisticated coronagraphs will empower the Webb telescope to examine smaller planets that more closely resemble Earth. New spectrographs are poised to deliver a higher resolution analysis of the chemical makeup of alien atmospheres. Furthermore, advanced techniques in image processing will allow scientists to pull more information from existing observations, possibly uncovering biosignatures that currently lie just beyond our ability to detect them. This observation campaign signifies something more profound than a mere scientific endeavor. It is humanity's first organized effort to chart the prevalence of life throughout our galaxy. It is conceivable that within the next decade, we could identify hundreds of worlds teeming with life, each possessing its own distinct biosignature and following its own unique evolutionary path. The universe might soon show itself to be not only a place where life can exist, but a place where it is abundant. Ultimately, this next campaign aims to resolve the most significant question in all of science: are we alone? The emerging evidence suggests a powerful negative, and we seem to be on the cusp of learning just how much company we truly have in the cosmos. The debris disk that encircles the star, Ce presents a cosmic spectacle of 3 distinct rings, with each one holding different kinds of materials at varying stages of planetary development. What this organized configuration reveals is that the formation of planets is not a haphazard event, but instead adheres to foreseeable patterns that bring order out of cosmic chaos. The 3 rings around Ce can be seen as separate chapters in the narrative of how worlds are made. The innermost ring, which is nearest to the star, is composed of the most delicate dust and the smallest rocky pieces. This material is warmed by the star's radiation to temperatures capable of melting lead, yet it holds a steady orbit within a slender band only a few million miles from the stellar surface. Within this ring, particles are in a constant state of collision and fusion, incrementally forming larger and larger bodies that will one day serve as the cores for rocky planets. The middle ring, which is home to the newly found planet, contains a blend of rock and ice that tells the story of a world currently taking shape. This is the region where conditions are ideal for both rocky and icy substances to coexist, fostering the kind of complex chemistry that can give rise to habitable worlds. The planet discovered here has swept its orbital path mostly clear of the original material, but the debris that remains provides evidence of its ongoing accretion and expansion. In the outermost ring, we find the system's most untouched material. This ring is made up largely of water ice and organic compounds that have been frozen since the star first formed. It functions as a vast repository of volatile materials that could eventually be transported to the inner planets through gravitational disturbances or collisions. The outer ring signifies the deep freeze of planetary formation, a place where the essential ingredients for life are kept in a state of preservation. The distance between the rings is not arbitrary. It conforms to mathematical relationships that expose the gravitational framework of the entire system. Each ring settles into a zone where the principles of orbital mechanics foster stable conditions for matter to gather. The empty spaces between the rings are areas where gravitational resonances would destabilize orbits, thus preventing material from collecting and forging the clean divisions that keep the rings separate. The three-ring configuration also lays out a clear timeline for how planets are born. The innermost ring illustrates the very first stages, where tiny dust grains are just starting to adhere to one another. The middle ring signifies an intermediate phase, where objects the size of planets are actively clearing out their orbital domains. The outer ring demonstrates the preservation of the system's original matter, awaiting the proper circumstances to start its own journey toward becoming a planet. Computer models of the C-Antliae system indicate that this three-ring arrangement is not a fixed state but is instead evolving through time. Material is gradually spiraling inward from the outer rings, which in turn feeds the development of planets in the inner system. The newly discovered planet serves as a gravitational gatekeeper, moderating the flow of material from the outer rings to the inner one, and establishing a controlled delivery process that permits planets to grow at a steady pace over millions of years. The trio of rings around C-Antliae is more than just an elegant cosmic feature. It offers a direct view into the universal mechanics of planetary formation. Similar ring structures have been noted around other young stars, which suggests that the organized progression of planetary birth follows comparable patterns across the galaxy. We are not merely observing a single stellar system. We are witnessing the universe as it manufactures new worlds. The planet identified by the James Webb Space Telescope within the C-Antliae system has set a new and fundamental record in the field of exoplanet science. With a mass that is only 1/3 that of Jupiter, this world stands as the least massive planet ever to be directly imaged orbiting another star. This accomplishment is more than a simple technological benchmark. It proves that the Webb telescope is capable of detecting and studying worlds that bear a striking resemblance to the planets within our own solar system. In the past, the direct imaging of exoplanets was restricted to enormous worlds, generally many times more massive than Jupiter. These so-called super-Jupiters were simpler to spot because their immense size and high temperatures made them luminous enough to be seen against the overpowering glare of their host stars. However, the recently found world around C-Antliae is 10 times less massive than any planet previously imaged, effectively pushing the limits of what is achievable with our current technology. The planet's small mass introduces significant difficulties for detection. Planets with less mass are naturally cooler and fainter, which makes them exceedingly hard to separate from the brilliant light of their parent star. The light emitted by this particular world is nearly 10 billion times dimmer than the light from C-Antliae, a fact that demanded the Webb telescope to perform at the very edge of its sensitivity. The ability of the telescope to register such a faint object is a testament to extraordinary engineering and sophisticated data analysis. Yet, the planet's low mass is also what makes it so compelling from a scientific standpoint. Celestial objects with masses in the range of Jupiter's mark a crucial dividing line in planetary formation, separating the gas giants from the smaller, rockier worlds. This particular planet sits at a fascinating boundary, the dividing line between large gas giants and smaller, terrestrial worlds, offering crucial clues about how planetary systems shift from one type to the other. Understanding this transition is fundamental to predicting where habitable planets might arise. The planet's mass is also a key factor in its potential for habitability. While worlds the size of Jupiter are typically gas giants lacking a solid surface, this much lighter object might have a solid core wrapped in a relatively thin atmosphere. Its surface temperature of roughly 120 degrees F indicates that the planet holds on to enough atmospheric mass to sustain a greenhouse effect, but not so much that it would have become a runaway gas giant. The detection of this low-mass world required truly innovative observational approaches. The infrared instruments on the Webb telescope had to distinguish the planet's weak thermal signature from the much more intense scattered light from dust in its debris disk. To accomplish this, advanced image processing algorithms were employed to filter out the contaminating light from the star and disk, which finally revealed the planet's faint infrared glow. The entire process is akin to isolating a single, quiet note within a cascade of noise. The planet's low mass also makes it an excellent subject for future atmospheric research. More massive planets possess thick atmospheres that can obscure their deeper layers from observation. By contrast, this world's thinner atmosphere permits Webb to probe deeper into its composition, which could unveil details about atmospheric chemistry that are impossible to discern on more massive planets. Perhaps most importantly, the discovery of this low-mass object demonstrates that Webb is capable of finding and studying planets genuinely similar to those in our own solar system. This opens the door to discovering and analyzing truly Earth-like worlds, bringing us nearer to finding planets that may not only be habitable, but are actually inhabited. The lightest world ever imaged has started a new chapter in the search for life beyond Earth. The discoveries made by the James Webb Space Telescope represent only the start of what will be a transformative era in the quest for extraterrestrial life. Planned observatories and technological progress over the next 2 decades are set to revolutionize our ability to detect and examine life on distant worlds, potentially unveiling a universe teeming with biological activity that extends throughout the entire galaxy. The most ambitious of these future projects is the Habitable Worlds Observatory, a space telescope designed specifically to detect and analyze Earth-like planets orbiting Sun-like stars. This observatory will use advanced coronagraph technology to attain contrast ratios of 10 billion to 1, allowing it to directly image planets that are truly comparable to Earth. The telescope will be capable of identifying the atmospheric signatures of oxygen, water vapor, and other biosignatures that could point to the existence of life. Ground-based observatories are also expanding the boundaries of what is possible. The extremely large telescope, currently being built in Chile, will have a mirror over 100 feet across, nearly 5 times larger than Webb's primary mirror. This massive telescope will be able to analyze the atmospheres of nearby exoplanets with unprecedented detail, potentially detecting dozens of different molecular species that could indicate biological activity. But the future of life detection extends beyond just building bigger telescopes. Artificial intelligence and machine learning algorithms are being created to analyze the vast quantities of data these observatories will collect. These systems will be able to recognize patterns in atmospheric chemistry that may be too subtle for human observers to see, potentially identifying life forms based on a completely different biochemistry than what we find on Earth. The next generation of life detection will also focus on what scientists refer to as agnostic biosignatures. These are chemical signals that could indicate life without requiring assumptions about how that life functions. Instead of seeking specific molecules like oxygen or methane, these techniques will search for patterns of chemical disequilibrium that could only be sustained by active biological processes, regardless of the specific biochemistry involved. Perhaps most exciting is the development of technologies that could detect life in real time. Future observatories will be able to monitor changes in planetary atmospheres over hours and days, potentially observing the collective breathing of entire biospheres. These observations could reveal not just the presence of life, but active biological cycles that respond to planetary rotation, seasonal changes, or other environmental factors. The future also holds the possibility of detecting technological civilizations directly. Advanced observatories will be sensitive enough to detect the atmospheric signatures of industrial processes, artificial lighting on the night sides of planets, and other signs of technological activity. The search for extraterrestrial intelligence will become a routine part of exoplanet characterization, potentially revealing not just life, but civilization throughout the galaxy. Within the next 20 years, we may have identified hundreds of living worlds, each with its own unique atmospheric chemistry and evolutionary history. The universe may reveal itself to be not just habitable, but abundantly alive, with biological processes operating on scales that dwarf anything in Earth's history. The future of life detection promises to answer humanity's greatest question: are we alone? The answer appears to be a resounding no, and we are about to discover just how much company we have. The moment will come without fanfare. A scientist in a laboratory will look at a computer screen showing data from the James Webb Space Telescope and realize that humanity's cosmic loneliness has ended forever. The evidence will be undeniable, a combination of atmospheric signatures that can only be explained by the presence of life, actively transforming the chemistry of an entire world. In that instant, everything will change. The discovery of life on K2-18b has already brought us to the threshold of this moment. With 99.7% statistical confidence, we have detected the chemical signatures of biological activity 120 light-years away. The dimethyl sulfide in the planet's atmosphere, the complex interactions between methane and hydrogen, and the chemical disequilibrium that can only be maintained by active biological processes all point to a world where life is not just present, but thriving on a planetary scale. Yet, the point of absolute conviction will arrive only when a variety of separate observations corroborate what is already strongly believed. Multiple telescopes will need to register the same biosignatures, while alternative explanations are methodically dismissed. The statistical certainty will climb from 99.7% to 99.99%, and ultimately to a level of proof that leaves no room for reasonable doubt. When this moment comes to pass, its ramifications will resonate through every facet of human society. Science itself will undergo a revolution, forced to contend with the reality that biology is not an anomaly of Earth, but rather an intrinsic characteristic of the cosmos. Our philosophical and religious frameworks will be transformed as we are compelled to re-examine humanity's role within a universe that harbors other living things. Technological progress will accelerate dramatically as we devise novel approaches for studying and perhaps even communicating with life on far-off worlds. The psychological effect on the human species will be immense. The realization that we are not by ourselves will finally put an end to the cosmic solitude that has shadowed our species since we first gazed at the stars, questioning if anyone was gazing back. We will find our place as members of a galactic collective of living planets, each tracing its own unique evolutionary journey, yet all sharing the foundational experience of existence in the universe. This moment, however, will also usher in new responsibilities. As we begin to identify a greater number of inhabited worlds, we will be confronted with ethical dilemmas concerning our duty to safeguard and sustain life across the galaxy. The confirmation of extraterrestrial life will compel us to forge new paradigms for comprehending our connection to the cosmos and our obligations as a species capable of space travel. The instant we know we are no longer alone will signal the dawn of a new chapter in the human story. We will shift from being a species that merely speculates about life elsewhere to a civilization that knows it is present throughout the galaxy. The cosmos will be redefined in our minds, changing from a vast, barren expanse into a cosmic ecosystem vibrant with biological processes and evolutionary trials. Reflecting from that future vantage point, we will see the James Webb Space Telescope's detection of biosignatures on K2-18b as the inaugural step on humanity's path from cosmic seclusion to galactic belonging. The chemical traces found in the atmosphere of a planet 120 light-years distant will be chronicled as the evidence that concluded our solitude and initiated our comprehension of our place within a living cosmos. The moment we are no longer solitary is nearly upon us, and everything is on the verge of transformation. We are poised on the precipice of the single most significant discovery in the history of humankind. The James Webb Space Telescope has gazed across a distance of 120 light-years and uncovered something that promises to alter all our previous conceptions about our position in the universe. Within the atmosphere of K2-18b, a world enveloped in hydrogen clouds and heated to a precise 120 degrees F, life appears to be respiring. The evidence is compelling. Dimethyl sulfide, a molecule that is exclusively produced by living things, is present in concentrations substantial enough to be detected over interstellar distances. The level of statistical confidence stands at 99.7%, a figure that rivals the certainty of any established scientific fact. What's more, the atmospheric chemistry suggests a narrative of biological functions at work on a planetary scale, reshaping the very air of an entire world through the combined respiration of innumerable organisms. Yet, K2-18b is not an isolated case. The Webb telescope has unveiled a cosmos where worlds capable of supporting life are plentiful, with each one presenting a distinct set of conditions for life to arise and flourish. From the swirling debris disks surrounding young stars where new planets are taking shape, to the vicinities of ancient red dwarfs destined to burn for trillions of years, the galaxy seems to be replete with environments where life could not just endure, but thrive. The ramifications of this discovery reach far beyond the discipline of astronomy. We are observers at a historic juncture, the conclusion of humanity's cosmic isolation and the dawn of our awareness as participants in a galactic community. The universe, it seems, is not a void dotted with infrequent oases of life. Rather, it is an immense ecosystem where biological activity unfolds on scales that eclipse anything known in Earth's own history. The very technologies that enabled these findings are merely a prelude to what is to come. Future observatories are poised to uncover the atmospheric fingerprints of hundreds of other living worlds, each possessing its own distinct biochemistry and evolutionary trajectory. It is conceivable that we will encounter forms of life founded on chemistries entirely different from our own, which would dramatically expand our definition of what life is and the ways in which it can begin. The instant we can definitively confirm that we are not alone will represent a pivotal moment for human civilization. Every child brought into the world after that confirmation will be raised with the innate knowledge that life is present across the galaxy and that we belong to a cosmic fellowship that extends across the stars. The philosophical and spiritual consequences will echo through every part of human culture. Perhaps the most significant insight, however, is that these findings suggest life is not merely possible in the universe. It appears to be an inevitable outcome. It seems that wherever the proper conditions exist, life takes hold and begins to reshape its world. The chemical signatures identified by the Webb telescope are more than just evidence of biology on a faraway planet. They are an indication that the universe itself is, in a fundamental way, alive. The James Webb Space Telescope has offered us our first true look at our cosmic neighborhood, showing us that we inhabit a galaxy where life is not the exception, but the prevailing rule. We are not alone now, and in truth, we never were. The cosmos has simply been waiting for our species to create the technology capable of perceiving what has always been present. It is a cosmos abundant with life, breathing in cadence with innumerable biospheres, and vibrant with possibilities that we are only just starting to comprehend. The universe is alive, and we are an integral part of its unfolding story.